finish the graphs.
Okay. All right, so let's do a quick review. Did I have you working together? Did you do any work together?
No.
Okay. All right, and here's what I want to do right now. First of all, I want to give you a rundown of how things are operating. You'll see on the board there, there's some stuff written there that pertains to you. Monday, your homework is due 1/5 to 1/7. Tuesday is our test, and that's when your review work will be due. This time there are 3 review things due. Review sheet 1, review sheet 2, and something called practice test, which you already have. It's all in the packet. You have it all. Once again, I am making the book assignment. There's also a book assignment listed on your assignment sheet. I'm making that optional. Those are problems you can do if you need extra practice, but you don't have to. All that's due Tuesday. So obviously, you should be working on that review work, like starting now. We're not quite done. But we have to do 1/7, and then we'll be ready to do that. All right, so we have a test on Tuesday, 1 week from today. Your homework is due 1/5 to 1/7. Those assignments are due on Monday. Should have been due Friday, but we don't have school that day, so you get the whole weekend. So it's due on Monday. And then your review work will be due when you take the test, just like always. All right, everybody good with that?
Is the E-Day just going to be reviewed then?
Yes, for us, the E-Day will just be review, because that's what we're missing. We would be missing a review day, so it'll just be review, which I'll have a video posted if you want to access it. If you don't, I'll probably be doing the review sheet on the video. So if you want to access it, great. If you want to do it on your own, that's fine too. But there won't be like a separate assignment, because that's not where we're at right now. We're at reviewing. Okay, so we good on that? All right, so I want to just do a quick, brief recap of all these transformations, because we've learned a lot of transformations. So let me make up a shape. Actually, you know what? Instead of making, well, maybe I will make one up. Let me make up a shape. We'll call this f of x, and it will be, let's say, a trapezoid and 2 semicircles. All right, so that's our shape, just our random shape. Now, we've talked about a lot of things that we can do to that shape, right? What are some things we can do to it? Alec?
You can make it bigger.
We can make it bigger or smaller. And we can do that this way or this way. And what do I do to my equation to make it bigger or smaller? I multiply something, right? So if I were to multiply by a half, let's say, what would that do to this picture? It would make it half as tall. Remember, this number multiplies the vertical. So I'm going to be half as tall as I was. So see that trapezoid right there? He used to be 2 tall. Now he's only going to be 1 tall. He's the same trapezoid, but he's only 1 tall. See these 2 little circles? They're 1 deep. Now they're only going to be half deep. As opposed to that multiplier. Both of those are coefficients. Both of them are multipliers. What does that one do? Divides the horizontal. Remember, anything attached to x does the opposite of what you think. That's just one of the weird things about math. Anything you attach to x does the opposite. So it looks like that's 1/2 times x. It's divided by a half. Not times a half, divided by a half. And divided by a half is the same as what? times 2. So this picture is going to be twice as wide as it was before. So how wide is that trapezoid? 3. So now it's going to be 6. Now it's the same height, so it's the same height as it was, but now everything that was 1 step is now 2 steps on. And see my little semicircles? Each of those is 2 wide. Now each one of them is going to be 4 wide. So there's the first one. There's the second one. Braden?
So if that was like, instead of half, it was 2, it would be like, it'd be half.
Yep, it'd be half as wide.
Okay.
So these guys, instead of being 2 wide, they'd only be 1 wide.
Okay.
All right, so yes, somebody said, Alec I think said, we can change our problem by multiplying by something. All right, and what does multiplying do? Change the size. All right, what else can we do to our equation besides multiplying? We can flip it, which means what would be in the equation? What do we put in the equation to flip it? Negatives. So we can put a negative, just like we could put our 1/2 in different spots. We could put a negative outside like this, or we could put a negative inside like this. You gotta know this, you gotta keep it straight somehow. What does that one do? X-axis, exactly. It flips it over the x-axis. I think of this one as the upside down one, but that's up, I mean, it's over the x-axis. That's what happens. So I'm gonna redraw my picture, this exact picture, exact size, nothing's changing that way. I'm gonna redraw it, but upside down. There it is. What about that one then? Well, obviously, if this one is the x-axis, that one's going to be the y-axis. It's called a reflection or a flip. So we're going to take that picture, and instead of drawing the trapezoid over here on the right, I'm drawing the trapezoid over here on the left. And my 2 little circles will be over here on the right. Okay, what else can we do?
Absolute value.
What?
Absolute value.
We can do absolute value, and like all these, we can absolute value the whole problem, or we can absolute value just the x. Okay, so who remembers what absolute valuing the whole problem does? Makes everything positive. So in other words, everything has to be above the x-axis. So the trapezoid's already there, so that's not an issue. But these guys need to be made positive. So they need to be folded up. So that is a picture of the absolute value of the whole problem. Now, what happens when I absolute value just x?
Is it going to be the same
The right side.
both sides?
Right side and left side are going to match. So you go back to your original picture. The right side stays the same, and it's duplicated on the left side. So that would be a picture of the absolute value of x. And you say to me, well, Miss Ford, what happened to the circles? Gone. Gone. When you do the absolute value of x, this disappears. All right, there's one more thing we can do. We've hit them. multiplied, we put in negatives, and we've absolute valued. What is the other thing we can do? Add and subtract. So once again, we can add and subtract to the whole thing, or we can add and subtract to just the x. All right? What does that do? Up 3. So it's going to take your picture that started at the origin, and now it's going to start up at 3. You're going to draw your trapezoid up 3. There he is. And then you're going to draw your circles. There they are. Is that okay with everybody? Now what does that do? This takes you to the left 3. So the whole picture is getting moved to the left 3. So the trapezoid that used to start at the origin is now going to start back 3 steps, which, because of its size, is going to make it look just like that. And of course, then these guys, there it is, backed up 3 steps. Everybody okay with that? All right. Now I need you to do something for me. I need you to get out a piece of paper that you don't care if it gets ripped up. So don't make it a valuable piece of paper. We're going to be doing some arts and crafts. Probably the one time all year. Getting out your paper. Everybody got a piece of paper? Now, are we all starting with roughly the same size paper? Everybody using this sheet of notebook paper or something, writing paper, whatever? Good, because something really cool is going to happen. All right, here's your job. All right? I want you to rip out, if we had scissors, that'd be great, but we don't, so we're just going to rip. I want you to rip out squares from each corner of the paper. Now, the squares, I want the squares to be the same size, but my squares don't have to match your squares. You can do bigger squares or smaller squares than me, but all of my personal squares have to be the same size, okay? Oh, you have scissors. Aren't you, Johnny, on the spot? So cut out your squares from your corners. Everybody's cutting them out. Whatever size you want, take out your squares. And we're going to make sure all of our paper gets put in the recycle, okay, when we're done. But you're cutting out little squares, big squares, whatever, from the corners of your paper. Everybody's doing it. Okay, we got our squares cut out. You guys are slow. This isn't for grade, so it doesn't have to be perfect, okay? Just do your best. And as soon as you get your squares cut out, I want you to do this. I want you to fold up the flaps that you have created. See how I'm making folds here? I want you to fold them all up. And you are then going to have a handy-dandy little box. Okay. So, Another sheet of paper.
Oh my.
You what now?
Here you go. See how we took out of each corner? That's what you want to do. All right, so you fold it up. When you get your box made, hold it up so we can all see each other's boxes. All right, Blakely and I have a perfect example. She's the first one with her box up. Or Alec and Blakely, perfect example. They both started with exactly the same size sheet of paper. But look at their boxes. Are they gonna hold the same amount? Like if I had, let's say, some M&Ms and I started filling Blakely's box with M&Ms and then I walked over and filled Alec's box with M&Ms, would they hold exactly the same number? No. The boxes are different sizes. What made them different sizes? Look at these two. Look at that. See how different they are? What made that happen?
The different squares.
Oh, the size of the squares we cut out determined the size of the box that we ended up with, right? One of the classic problems in calculus, and I mean it, it's a biggie. This is known as the box problem, is to maximize the volume of the box. In other words, figure out what size square would make the biggest box possible, the box that would hold the most. And like he said, it's totally dependent on the size of the squares you cut out. So let's look at that from a calculus standpoint. Now, we aren't going to actually do the problem by hand. We're going to allow our calculator to do it. But when you get to your calculus class, you will do this problem by hand. And it's very easy. You'll have no problems. So here's our piece of paper. How big would you say our paper is? Is it like, what, 8 by 11? Well, I'll go the other way. How about that? 8 by 11, I think, probably, something like that. And you cut corners out. We don't know how big they are, but they determine the size of the box. And then we folded up these flaps here. Can you visualize those flaps folding up and making the box? So this is like the bottom of the box, right? Now, our job is to find the maximum volume. Okay? How do you find the volume of a box? Length times width times height. Okay? So let's look at the length of your box. It started out at 11, but what did you do to that 11? You took an X from this side and an X from this side, right? So that's 11 minus 2X for my length. We didn't do this already, did we? 11 minus 2X. What's the width of my box going to be? 8 minus 2X. Here's the tricky one. What's the height of my box going to be? Look at your box. How tall is it? Isn't this how tall it is? So its height is X. Because you folded up the flap and the flap was X big. I worked on your test yesterday. Question number 1. Right here. It's a 3-part question like it always is. Number 1, write the equation for the volume of the box. We've done that. Number 2, what's the domain? Now the reason this is important, particularly important for us, is we're going to graph this on our calculator, and we need to know which part of the graph to look at, because the whole graph doesn't make any sense. Think about X for a minute. There are boundaries for X. X has to be between something and something. Can you tell me what X has to be between in this problem? Can X be negative 100? No. What's the smallest it can be? It has to be bigger than 0. Now, X can't equal 0 because if X were 0, you wouldn't be cutting any corners out and you wouldn't be able to make a box. So it can't be 0, but can it be like a tiny little number like 0.1? Yeah, you could take out tiny little squares. All right, now, can X be 100? Why not? Has to be less than. Okay, I'm liking the thought it has to be less than 8 because the paper's only 8 big, but it's worse than that, people. You're taking a piece off both ends of the 8. So it couldn't be 7, could it? X can't be 7. What does it have to be? Less than 4. X has to be less than 4. Now think about it. Your paper's only 8 across. You're taking a chunk off both sides. Is he awake? How come your eyes are shut and your head's back? Sit up. You're hurting my self-esteem. This is 8. If you, yeah. I didn't say your name though, Alec Major. We have 8 units across, and we're cutting a chunk off both sides. The chunks can't be bigger than 4. Now, why is that important? Because when I go to graph this on my calculator, because I want a maximum, so I'm going to graph it and find a maximum. But when I do that, this is X min, and this is X max. I don't want to look at anything else in this picture because this is the only part that makes sense, right? For this particular problem. All right, so let's get our calculators out. And I'm going to graph this equation. Oh, by the way, you can put it in your calculator just like this. Make sure you're putting in the parentheses. When you do this in your calculus class and you're doing it by hand, then you'll need to FOIL it all out and get it in its polynomial form. But this is perfectly okay for the calculator. So my window, X min is 0, X max is 4. What about Y min? What does Y stand for in this problem? What's your Y? It's your volume. What's the smallest a volume can be? 0. So Y min is going to definitely be 0. What about Y max? No idea. That's the question, isn't it? So pick a number. Now, whatever number you picked, one of two things is going to happen. You're going to see on your screen, you're going to see this. Actually, you're going to see this, which is what you want to see. Or you're going to see this, which means what? It's not big enough. You're going to have to make it bigger. You need to see the top of the hill. I used 100 for my max, my Y max, and it works great. Then we're going to find the maximum. Do you remember how to do that? Second calc, choose max, set your bounds, take a guess, and my maximum worked out to be 1.525, 60.013. Is that what yours looks like?
No. I'm not even getting like a graph. Like no like arc on mine. It's just
Okay,
like
well how was your window set?
my window for x min is 0 and x max is 4.
Mm-hmm.
And then for y min is 0 and for y max is 10.
Okay, 100.
Sure.
10 is not big enough.
I'm still not getting anything.
What's your equation?
Oh, I didn't put an equation in it.
Oh, well, that would be the reason we're not getting a graph. Yes, we have to have an equation put in
Is it
order to
that?
get a graph. Yes,
Oh,
this is the,
yeah.
yeah. All right, now, every time we do this, we get a two-part answer. You get a point, your maximum point. In this case, the question was find the maximum volume. So which piece of this, the X or the Y, am I interested in? What? This is the Y right here, right? That's my Y. So that's the volume right there. What's that represent? What's the 1.5? That's how big your squares should be. So if the question said, find the size of the squares, the answer would be 1.5. But since the question was find the maximum volume, the answer is 60. Okay? Now, we're going to go to lunch, but here's what you have to do before we go to lunch. As soon as you bring me the correct answer, you can go to lunch. Here is the question. I want you to find the dimensions
the rest of your life, man.
of the largest box you can make from a piece of cardboard that's 20 by 30. 20 by 30 inches. Now, you're finding the dimensions. All right? You're going to do this exactly how we just did it. The only difference is this is 30 and this is 20. So you're going to write an equation, you're going to give me the domain, and you're going to give me the answer. What's the equation? I'll help you out here because otherwise we'll be here forever. What's the equation?
30 minus 2.
30 minus 2x times 20 minus 2x times x. Volume is length, width, height. You got to have all three. All right? The domain you worked for the last problem is not going to work for this one. You need a new domain. You need a new x, min, and max. Now, do we still have 0 as the lower limit for x? Yeah. Will that always be the case? Yeah. But what's your upper limit now? 10. Because your smallest dimension is 20 and you're cutting it from both halves. So it's 10. Now, remember the question. So you should have something by something by something as your answer. So as soon as you bring that to me, you got to give me a minute to do it though. As soon as you bring it to me, you can go. I'm going to turn off the radio. Oops, somebody's wallet's on the floor.